Unit 5, Progress Check, FRQ B, question 2. So now we are mosquitoes in a field after a major rainfall. And in this case, we are given a function of the number of mosquitoes. Use the correct units to interpret the meaning of this. And I can tell you this, what they're looking for. I might have worded it slightly different than them, but there's 4 key elements. You need to say specifically what time it's happening at. So the 15 with units need to be somewhere. You could have put it at the end of the sentence. You also need to have the number of mosquitoes in the field after a major rainfall. That's the context. That needs to be there, right? You need to say what is happening. So it's decreasing. That's the negative part, right? Decreasing at a rate. The word rate has to be there. At a rate of 171. So I said decreasing, then you can't have a double negative. So you can't have decreasing and then a negative 171. So either you would say changing at a rate of, that would work, or you say if you say changing at a rate of, then you would have to say negative 171. If you're saying decreasing at a rate of, then you use a positive here. And then you need to have the units as well. So here are the units, mosquitoes per hour. Not mosquitoes, it's a rate, right? And I can use this color here. So these are the 4 major things that have to be there like we discussed. Did they do it slightly different than me? They might have. Let's see here. At time t is equal to 15 days, the number of mosquitoes in the field is decreasing. Oh, it's almost verbatim the same as me. I just wrote the word when. Or you could have it at t is equal to 15 days at the end of the sentence also works. So, but those 4 elements have to be there in some way, shape, or form to get full credit for that one. All right, part B, it says, based on the model, what's the absolute maximum? Now, there's lots of different ways you can address this. First of all, you have to find the critical numbers. So you got to find the derivative, set the derivative equal to 0, and then solve for t. In this case, when I solved for t, I got t is equal to 12 and negative 4. But negative 4 is not in the interval we're interested in. We're in from 0 to 18. So therefore, we're just going to use the 12. I test the critical number and the endpoints. In this case, I know that the m of t is continuous because it's a polynomial function. So essentially, I'm going to use the EVT, the extreme value theorem, to help me sort of prove or show this. So I'm showing that m of t is equal to, or m of 12 is equal to, when you work it out, 1728, and the endpoints are 0, so I have to find m of 0. I did it in a table down here, but it works the same. M of 0 is this one, showing the substitution. Then for the 12, testing that, and then testing the other endpoint down here on the end for 18. I got a value. Oh, where am I getting the maximum value? That's 1728. So essentially, I know that it's a closed interval. I know the function is continuous. So by the extreme value theorem, I know that it's either going to be at the endpoints or at a critical number. So in this case, it happens to be at the critical number. So the absolute maximum value of mosquitoes in the field over the time interval from 0 to 18 is 1728. And by the EVT, we know that m of 12 is the absolute maximum of that. Now, I think they did it slightly different. They showed and justified that you have a local maximum by showing what happens to the left and to the right. It changes from positive to negative. And then they tested or said that they tested the endpoints, but they didn't show that explicitly. So I feel like the explanation that I choose is a little more concise and a little more precise than what they have. This meanders a little bit, but if you didn't think to use EVT and you did it slightly different, as long as you have to discuss the endpoints for some in your justification. So they're looking for the first derivative, set the first derivative equal to 0, identify that t is equal to 12 as a candidate. Those are the 3 points. The justification, the second part of that, where I'm talking about the EVT and testing the endpoints, that's actually just the 4th point. So if you messed up on that part, at least you're getting most of the credit for it. All right, part C. What values of t is the rate changing of the number of mosquitoes? So look, you got to be really careful how you read this, because what value is the rate increasing? So I need to figure out where the derivative is increasing. So I have to take the second derivative and see where the second derivative is positive. So we have to take the second derivative. So basically the derivative of the derivative got me negative 6t plus 24. Set that equal to 0. That happens at 4. Test values, I showed the testing values, or you could have written it as an inequality in this case because I'm just looking for where this part is greater than 0. So that's another option. And then you write a sentence. The rate of the mosquitoes of the rate of change of the number of mosquitoes is increasing on the interval from 0 to 4. The last one I think confused, let's see what they did. Hang on. Part C. So, considering getting the second derivative, key idea, right? Finding the actual second derivative and setting it equal to, like here, either setting it equal to 0 or testing it or writing it as an inequality. Either way, that's like this part here. And then writing your answer. So make sure you write the answer to the question they were asking. All right, for part D, the number of bats in the field is modeled by the differential equation B, where B is a function of the number of mosquitoes. So a function of, that's B of, and the number of mosquitoes was M. So that's how we get this, that's really what the expression is, right? Now it's asking you to, based on the model, write an expression for the rate of change of the number of bats in the field at t is equal to A. So you take, that's just a chain rule. It's just a play on the chain rule. B prime of M of A times M prime of A using the chain rule. Don't forget to take the derivative of the interior. It's like layers of an onion. And then once I've done that, okay, I know what M of A is, substitute it into the M function. And I know what M prime is, prime of A would be, and substitute that into the derivative function. That's what I got there. And there we have it. So what do we got for part D? Yeah, so it's a one-pointer here. This is where you end up with this. Okay, so it should include the correct expression, so it's not even saying that you need to have a sentence form for that.